or be told some prior. Okay, so welcome back to the second part of our lecture, or the second major part of our lecture. And just as a recap, we were talking about Bayesian decision making, and we got to the Bayesian minimum error rule here. So conceptually, so far we've got to the point where if we can build a probability model P of x given omega, and we can estimate or be told some prior probabilities P of omega, then that allows us to estimate this P of omega given x, and then that allows us to make a decision on that basis. But this has so far been a bit generic, and we want to try and tie this down to something practical that we're going to make this decision on. And so what I'll be coming on to in a moment is to look at the Gaussian or normal probability density as the thing that we want to make our decision on. But just before we get on to that, I'll introduce a couple of concepts related to what we were just looking at about making our decisions. So suppose that we, let's go back to this curve. Suppose that we were at this point where the red is higher than the green and the yellow, and we therefore decide, okay, we're going to make an assignment into class 1. It's clear that there is still a chance that given our x at this position, it could have been class 2 and it could have been class 3. So there is still some probability that we've made a mistake. And the idea around that is that we've got the idea of a local pointwise error. So the error at x, or the expected error at x, is 1 minus this maximum. So in other words, what we're doing is we're summing up all of the classes that could have had an error, or alternatively, we take 1 minus the probability that actually we made the correct decision. So if our correct decision was made with probability 1, if I just go back to the previous slide, if we're right at this end, where the probability of omega 1 given x is close to 1, and the probability of all the other classes are close to 0, then 1 minus this is going to be very small. So at that end, this epsilon of x is going to be very small. But if we look in the middle, so again, going back to the previous slide, if we're in this middle point here, the sum of the probabilities of the other classes is going to be quite high, or 1 minus the probability of the red curve is higher. And so that's going to give us a higher chance of error there. And so that's going to give us our sort of local or pointwise error. And in order to work out the average error over all the possible points that we could have had, we take this value, this 1 minus max of P of omega j given x, we integrate that over all values of x weighted by its probability. So this is the expected value of this over all of the different points that it could have come from, and this gives us our so-called Bayes error. And the Bayes error is a theoretically lowest error that we can get in a system. So we can't get any smaller than that. We can rewrite it using Bayes' rule this way round if we want, because the P of x will multiply into this. It's the 1 minus the integral of the max of P of x given omega j, P of omega j dx. So this gives us this idea that if we've got certain classes with certain probabilities, just based on the overlap, no decision-making machine can have an error less than the Bayes error. And more practically, we'll often get worse than the Bayes error. And this will come up in the assignment, because there'll be some examples where you can see what would be the Bayes error for a particular setup. If your decision point was a different place, what's the actual expected error that would come up? And so here we can express it in a slightly different way as well. It's in terms of the class conditional errors and the average of those. So here we've got the averages over all the points. Here we've got the average over all the different classes. So there are different ways that we can view this. But the key point for this Bayes error is really that this is the theoretical minimum. It's a bit like if you're dealing with a communication system. A communication system has a theoretical maximum capacity. No matter how you design your code, how clever you are about putting something in, you can't put anything through more than a certain, the capacity of that, you can't get more bits per second through than the capacity of that channel. This is a similar idea for pattern recognition. If your classes are laid out as they are, you can't get lower than a certain Bayes probability. Yeah.
In computation, they say the capacity could be reached and the capacity rate could be reached. I mean, they could be equal, but in this Bayes error, can we do as well as the Bayes error?
If we estimate our classes correctly and the prior probabilities correctly, and we make the decision point at the point where the Bayes decision would be, then we would be able to reach the Bayes theoretical minimum error. But if our estimates are incorrect, and if we put our decision boundaries not in the correct place, then we will not be able to reach that. So it is possible to reach it, but we have to know the answers. We have to know the correct solutions in order to reach it. Okay, so up to this point, we've been talking about general rules. Now we're going to make it concrete by starting to talk about the Gaussian or normal distribution. And we'll also mention some others like k-nearest neighbor in a couple of weeks' time, and some other decision machines that you may come across later on. Some of you may have come across support vector machines, neural networks. All of these things, basically, they still apply the same thing, but they're other types of decision-making rule that we come up with. So what I'm going to focus on here is the Gaussian classifier, using Gaussian or normal distributions. You're probably most familiar. I'll write this out in a sort of easier form to start with. So general one-dimensional Gaussian, we have P of x given omega I is in one dimension 1 over square root of 2 pi sigma squared e to the minus a half of x minus mu I over x minus mu I squared over sigma squared. Actually, sigma I I'll use here because those are the ones that correspond to class I. So this is the one-dimensional distribution that hopefully you're reasonably familiar with here. Okay, here we've got the square root over 2 pi, and instead of putting sigma I squared with the square root over, this is just a slightly different notation for here. This is the one-dimensional version of our normal distribution or Gaussian distribution. The two-dimensional or multi-dimensional version, if we've got a real probability of x given omega I, and this is this time a vector x, should be omega, just draw it a little omega. So here for this one, this is 1 over 2 pi to the n, and the determinant of sigma I all square root, then e to the minus a half of x minus mu I transpose sigma to the minus 1 x minus mu I. Not sure if you can see that over there. Sorry, I went a little bit close to the back of the board there. But that's just writing this equation down in a different way. So expand some of this, these things in a moment to look at the where equal probability density curves and so on go from. But this sigma is the covariance matrix of a particular class. So it's the expected value of x minus mu I times x minus mu I transpose. And it's a real symmetric matrix. This value is real, this value is real. It's symmetric because this times it's transpose, so you can see that if you took the transpose of that, you just swap those and take the transpose. So it's clearly symmetric matrix. And it's that means that its eigenvectors and eigenvalues are nicely behaved. And we'll use these in a moment. So this is the distribution that we're going to be using a lot. If you're a bit rusty on multidimensional normal distributions or multidimensional Gaussians, then go back and do a bit of recap from that. But let's just visualize some of these so we can see how these look. And what I'll look at in a moment is to look at some equal probability density curves for these. So here's an example where the mean, mu, is 0. So here we have a mean at 0 here. The height is the probability density. And we're also drawing this in a sort of MATLAB where we've got a sort of color map with probability density dark blue is near 0, and the hot point in the middle of the sort of red points in the middle. And so that gives us that view from here. And here we've got a covariance matrix of 100 by 100, and that tells us roughly how widely spread this is. Now in this case, the covariance matrix is diagonal, with zeros off the diagonal. What does that tell us about the two components of that? Can we say something about their correlation between the two components? Yes, they're independent in this case and uncorrelated. In the general case, independence requires a stronger condition, but because we know that these are normal distributions, independent and uncorrelated is the same. So here's another example where the covariance matrix this time is got a larger component here than it has here, and that just tells us that the variance is stretched out in this direction compared to that direction. So we have a higher variance in that direction. How about the independence or correlation of the components? Are they now dependent or still independent? Yeah, they're still independent here because we've got zeros off the diagonal here, so they're still independent. And finally, this example here, where we've got the covariance matrix is no longer diagonal, we've got a covariance here, and so we can see that this is now tilted over. So it's the same extent in both axes, but we've now got a different diagonal. So here we do have a correlation between these two components. And this is something where it's going to be useful for us to find out the eigenvectors and eigenvalues. So just by eye, does somebody want to suggest the direction of one of the eigenvectors of this normal distribution covariance matrix? Yeah, 1, 1. So one of the eigenvectors is along this direction, the other one is along this direction. And if you wanted to solve this, you could actually check that 1, 1 is an eigenvector. So let's try it. We could go on the board over here. So 60, 40, 40, 60 multiplied by 1, 1 gives us 60 times 40 is 100. Where are we? 40 plus 60, another 100, which is 100 times 1, 1. So there we are. So we've got, it's an eigenvector, which means if you multiply by itself, it's a scalar times the vector. If you multiply a vector by that scalar times the vector, and this is our lambda in this case. That's the eigenvalue is 100. And if you want to check the other direction of 1 minus 1 is another eigenvector, and you can work out which one that would be. Anyone want to tell me what the eigenvalue for the other eigenvector is? Okay, we'll have a go. 1 minus 1, 60, 40, should come out about 20. Yeah. So that gives you an example of some eigenvectors and eigenvalues. Yes?
You just said independent is a stronger case than correlated.
Yes, that's right.
Uncorrelated. So you mean there are some cases that they are uncorrelated but dependent?
That's correct, yes.
Could you give an example? Also, I can't imagine.
Okay. Yes, let's. So let me give an example of an x1 and an x2, and they occupy a circular region here. So in this case, if my value of x1 is here, that tells me that my x2 must be in that region here. If my x1 is here, then my x2s must be in this band or this band. That means there's a dependence between x1 and x2. But if I were to measure a correlation between those two, because this is circular, there is no correlation. So if I just calculate a second order correlation, the correlation between these two would come out to be 0. So the reason that this doesn't happen for normal distributions is that normal distributions are completely determined by their second order statistics. So squares, correlations, and so on. This is not really part of the course, but this is sort of useful to know anyway. Whereas for higher order functions, for higher order statistics, so this strange ring shape isn't like that. And so therefore, correlation is a weaker condition to be uncorrelated than it is to be independent. So if I wanted to, the reason this is not independent is that P of xy is not equal to P of x, P of y. I can only have that if this were, for example, a square would be fine. That would have P of x, P of y, that would be uncorrelated, they would be independent. That would be okay. For the Gaussian example, if I go back to the previous one, this normal distribution, these are independent because the probability density for the whole thing is simply the product of the probability densities of the independent ones. And this allows us to simplify things when we're dealing with normal distributions, because a trick that we'll be able to use when we're dealing with these normal distributions is if we can find the eigenvalues, then that allows us to find out where the extent of things like equal probability density curves are. And I'll give some examples for that in a moment. So where this leads us on to for the Gaussian classifiers is using this decision rule. And actually, I think because this is something that I want to work through carefully, I have got slides here, but I'm going to go over to using the document projector to work through these examples more in longhand so that we can actually see where these come from. So let's switch over to the visualizer. So this won't be anything different to what's on the slides. I'll upload the visualizer examples afterwards, but I just want to cover a couple of things of why these Gaussians are so important. So the first thing is we saw some of these curves that I drew, ellipses of things. Actually, let's go back to the to the PC output to start with. So these ellipses, we can see on these curves, those represent equal probability density. It's a bit like equal heights on a map. So we think that these are aligned somehow with the eigenvectors. But can we show that? So let's just have a look and see why that happens first, and then we'll go over to the decision rules that we're going to make. So let's look first at the equiprobability, and I'll just fix the autofocus, equiprobability density curves. So we've got a Gaussian distribution, P of x is 1 over root 2 pi to the n, and determinant of our covariance matrix sigma, e to the minus a half, x minus mu, transpose sigma to the minus 1, x minus mu. Okay, so that should correspond to our probability density down here. And we want these equal probability curves, so we want the curves where p of x is constant. So some simplifications that we can make. We know that n, sigma, and 2 pi don't depend on x. So therefore, this thing at the bottom here, 2 pi to the n, determinant of sigma squared square root, is constant. So that means I don't care about the values here. I only care about where e to the minus x minus mu transpose sigma to the minus 1 x minus mu is constant. And e to the something constant, that just means I need to know where this is constant. So therefore, p of x is constant where x minus mu transpose sigma to the minus 1 x minus mu is constant. Now mu just sets the center, just sets the mean. So to simplify things, I'm just going to assume without loss of generality, which we could just written were log, we're going to assume mu equals 0. Alternatively, we can substitute, or x dashed is x minus mu. We can do a substitution if you like. So therefore, we want x transpose sigma to the minus 1 x equals constant. Now this is where we're going to start to use eigenvectors and eigenvalues to help us, because if we can break this down into the sum of constituent parts, that's going to help us to say what sort of shape we've got. So let's consider eigenvectors and eigenvalues of sigma. So we wrote that as sigma is u lambda u transpose, where our lambda is lambda 1, lambda 2, down to lambda n, and we've got zeros off the diagonal. So that's our diagonal matrix of the eigenvalues. This is lambda rather than lambda to the minus 1. So we're using lambda is a covariance matrix. So if you were writing these as one-dimensional ones, we'd use sigma squared, but sigma here is the whole covariance matrix. So I'm just finding the eigenvectors and eigenvalues of the covariance matrix. And because of that, that's equal to just the sum from I equals 1 to n of the dimensionality of lambda I ui transpose. So ui here are the eigenvectors that we're dealing with. So this is a decomposition of a square matrix, and we know this matrix is symmetrical. So we're able to decompose it into a sum of the eigenvalue in a particular direction and the eigenvectors in that direction. So if you're not familiar with this for square symmetric matrices, go back through the material for tutorial 2 and the linear algebra material. This is a very useful way of breaking up a symmetric matrix. But this is what we normally do, but we can also do that to the inverse, sigma to the minus 1. Because here, notice we've got sigma to the minus 1 rather than the forward matrix. And so we can break it down using just the same formulation, but this time our eigenvalues are inverted. U lambda to the minus 1, U transpose. In other words, the sum from I equals 1 to n of lambda I to the minus 1 ui transpose. This is why this is now going to be useful. Let me zoom in slightly so we've got slightly bigger and autofocus that back in again. Okay. So this is now going to be useful for us because now that gives us a way of unpacking this. So now we can say x transpose sigma to the minus 1 x is equal to x transpose into this sum from I equals 1 to n lambda I to the minus 1 ui, let's not get my u's and mu's mixed up, ui transpose x, which is equal to the sum from I equals 1 to n of x transpose ui transpose x. So that's just bringing the x's inside the sums here times lambda I to the minus 1. And this are both scalars. So this is a vector dot product, this is a vector dot product, and that's a scalar value. So now we've broken it up into a sum of how far is x along this eigenvector, and this is just its transpose, so it's the square of that, times the lambda I to the minus 1. So we can write that out as the sum from I equals 1 to n lambda I to the minus 1 x transpose ui squared. Or writing it another way, sum from I equals 1 to n of 1 over the square root of lambda I x transpose ui squared. And this formula, anyone recognize the formula for this shape? What sort of shape is this? It's not a circle. A circle will be the sum of x squared plus y squared is constant. What's this shape? It's an ellipse, yeah. So this is an ellipse with axes ui and half lengths square root of lambda I. So this tells us where those ellipse shapes come from. These equal probability curves are ellipses for a normal distribution or a Gaussian distribution. And if we go back, well, I won't go back for the moment, but if you go back to the slides, you can see those ellipse shapes come out. This is why it comes out. So this is a place where we've used the eigenvectors and eigenvalues to help us with this. Okay, so the next part that I'm going to move on to, now that we've seen what shapes these make, let's see what a Gaussian classifier does. If we use a Gaussian model for our classes, what type of decision rule are we going to come out with from there? So let's try, that's sheet 1. Let's leave that up there while we start on sheet 2. Let's build a Gaussian classifier. Okay, we're going to start again with our, just go out slightly, with our P of x given omega I is 1 over square root of 2 pi to the n determinant of sigma I, or square root of that, e to the minus a half, x minus mu I transpose sigma to the minus 1, x minus mu I. By the end of this module, you'll have got quite used to writing this equation. It comes up a lot. So we want to build a decision rule for this. Decision rule. X is assigned to class omega I if P of omega I given x is the maximum from all j equals 1 to m P of omega I given, omega j given x. So this is just the one that said this is our maximum a posteriori probability. If the probability of omega given x afterwards, this is the posterior probability, is the maximum over all of the ones, that's the class we're going to choose. So let's now work out what we want to calculate from Bayes. So we have this, P of omega I given x, but we're told P of x given omega I. So what are we going to use to get this in terms of this? Bayes rule. Yeah, so we're going to use this Bayes formula here. So from Bayes, this tells us that we want to use P of omega I given x is equal to P of x given omega I, P of omega I, over P of x. So, and we saw how we got Bayes before. So this thing here, which is the maximum over j of p of omega j given x. This was the thing that we had over here. This is the maximum over j of p of x given omega omega j, p of omega j over p of x. And we know that p of x is constant, so that's just 1 over p of x maximum over j, p of x given omega j, p of omega j. So our decision rule, because our p of omega I given x is the same as this without the maximum in there, we just multiply both sides by p of x. So our decision rule is now x is assigned to omega I. Yeah. So our decision rule is now x is assigned to omega I if p of x given omega I, p of omega I is equal to the max over all the j's from 1 to m of p of x given omega j, p of omega j. So we've lost that pesky p of x. We don't even need to calculate that. So now, p of omega given x, p of x given omega I, we know from here. So substitute p of x given omega I, we get p of omega I times, which is this bit, multiplied by this formula, 1 over root 2 pi to the n determinant of sigma I, e to the minus a half x minus mu I transpose sigma to the minus 1 x minus mu I equals the maximum over all of these, j equals 1 to m p of omega j times 1 over 2 pi to the n sigma I determinant square root e to the minus a half, slightly running out of space on that side, of x minus mu j sigma j to the minus 1, that should be transpose, and x minus mu j. Okay, and because 2 pi to the n is a constant inside the square root on both sides, we can cancel that. Okay, this is still a bit horrible looking. Well, let's get rid of this e by taking logarithms of both sides. Okay, we'll end up with a log of p of x, but it will at least simplify things a bit. So, actually, let's go on to another sheet to do that. So, sheet 3. Take log to the base e of both sides. We'll get the log. I'll write this as ln for natural log p of omega I times 1 over square root sigma I determinant plus, and then this term, which is minus a half x minus mu I transpose sigma to the minus 1 x minus mu I.
Is that second sigma to the minus 1, is that actually a sigma
Yes, you're correct. Yes, that should be a sigma I to the -1. And that's the same up there. Yes, thank you. So this is equal to the maximum value over the j's from 1 to m, p of omega j. This should be the log of log to base e of p of omega j times 1 over square root of determinant of sigma j plus minus a half x minus mu j transpose sigma j to the -1 x minus mu j. Now we can simplify this a little bit by saying, really, this term, this prior probability, and this 1 over sigma I, this sort of log term, is really a constant depending on the particular probability. So if we let Ci equals, and we'll multiply both sides by 2 to get rid of that half. So we'll say that's 2 times natural logarithm of p of omega I times 1 over square root of sigma I determinant. Then we get minus x minus mu I transpose sigma I to the -1 x minus mu I plus Ci is equal to the maximum from j equals 1 to m of minus x minus mu j transpose sigma j to the -1 x minus mu j plus Cj. And although this might look not quite so nice, really what this is, we can see here that it depends on x twice and some covariance matrices and so on here. So what this says is this is piecewise quadratic in x. So depending on which of these max values kicks in, it's made up out of quadratic curves. Can someone give me some ideas of some quadratic curves that you know? Parabola, yeah. Ellipse, circles, straight lines. So these are the sorts of things that will make up the decision boundaries. So I'll go on next week to simplify some of these things, but just very quickly before we take the break, going back to, well, the break, it's now the end of the lecture. There is now an assignment where you can start to have a go at this. You might want to start already, and you'll be able to start with here. This is not a computing example. There are some things where it talks about estimates from here, but the estimates that you make are based on, they would be an average, but actually you're told what the average would be, that it's slightly bigger, slightly smaller, and you use personal numbers. So you have in here, let's go to the other slide, there is a set of values. So look up your student number and you get your own personal values. So your answers are going to be slightly different to everybody else's. There is also a help sheet, which basically will help you to work through that example. That's due in week 6, so we've got plenty of time to do it yet, and I'll be going through more stuff next week. Anyway, thank you very much for listening so far, and I will see you next week. Bye for now.